Welcome back to the channel. This is the story of a massacre, a mystery that lasted almost 100 years, and the tiny fragment of DNA that rewrote the truth. In 1918, the execution of the Romanov family in Yekaterinburg left a void filled by legends, especially that of Grand Duchess Anastasia. But when the remains were found, science ran into a problem. A hidden genetic trait in Tsar Nicholas II called heteroplasmy threatened to nullify the entire identification. Get ready to dive into the forensic genetics that challenged history, and don't forget to leave your like and subscribe so you don't miss our next molecular mysteries. On the night of July 16th to 17th, 1918, in the basement of the Ipatiev house in Yekaterinburg, Russia, 3 centuries of the Romanov dynasty were ended. Tsar Nicholas II, Tsarina Alexandra, their 4 Grand Duchesses, Olga, Tatiana, Maria, and Anastasia, and the Tsarevich Alexei were brutally executed by a Bolshevik firing squad. What followed was not only the collapse of an empire, but the birth of a mystery that lasted for almost a century. The official history was quickly muddied by myth. The failure to identify all the bodies in the mass graves gave rise to romantic legends about a Grand Duchess or the Tsarevich who had somehow escaped. Anastasia became the central figure of this survival myth. While historians debated and imposters proliferated, the weight of historical certainty rested, ironically, on a field of study that did not even exist in 1918: forensic genetics. The promise of DNA was simple: dispel the myth and confirm the history. However, the path to the truth was anything but straightforward. At the heart of this search, a minuscule and unexpected hidden trait in the genetic code of Tsar Nicholas II himself, a phenomenon known as mitochondrial heteroplasmy, became the cornerstone of the identification. Far from being a simple finding, this genetic anomaly forced the scientific community to question its own protocols and, in doing so, revalidated the historical narrative with a molecular precision never before seen, closing the curtain on the last and most persistent dynastic enigma of the 20th century. The first major breakthrough occurred in 1991, when the remains of 9 skeletons were discovered in a mass grave near Yekaterinburg. History indicated that these should be the remains of the Tsar, the Tsarina, 3 of their daughters, and 4 of their servants. But which of the 5 imperial children were present, and which were missing? The shadow of Anastasia and Alexei remained a historical doubt. The initial identification was a monumental challenge. Skeletal and dental analyses could only offer preliminary identification. To achieve undeniable certainty, scientists turned to mitochondrial DNA, mtDNA. mtDNA is a small, circular genetic code inherited exclusively through the maternal line. This made it ideal for tracing lineages, as the mother, the children, and the maternal line of the grandmother would share the same mtDNA sequence. The key to identifying Tsarina Alexandra and her daughters lay in comparison with her mother's family. But for Tsar Nicholas II, researchers needed proof of kinship via the maternal line, which passes through the Tsarinas of the previous generation, or a relative who shared recent ancestry. The solution came from the British royal house. Prince Philip, Duke of Edinburgh, was Queen Victoria's great-grandson, as was Tsarina Alexandra. But more importantly, the Duke of Edinburgh was the grandson of Tsar Nicholas II's grandmother's sister, Maria Feodorovna, which meant they both shared the same mitochondrial DNA through Queen Victoria. By comparing the samples from the skeletons with Prince Philip's mtDNA, the identity of the Tsar, the Tsarina, and 3 of the daughters was confirmed with high probability. The mystery seemed solved. Or at least it was, until a genetic detail brought the scientific consensus to a sudden halt. At this stage of the mystery, the heteroplasmy of Nicholas II has us on tenterhooks. A simple change in mitochondrial DNA almost disqualified the Tsar. Before we reveal how scientists used his brother's DNA to prove his identity, I would love to read your opinion. Do you think survival myths like Anastasia's are more appealing than historical truth? Leave a comment with your theory. And if you are enjoying this intersection of history and forensic science, support me by giving a like and sharing this video. The analysis of the mitochondrial DNA from the skeleton identified as Nicholas II presented a finding that did not fit the rule. It showed not 1 but 2 slightly different mtDNA sequences at the same position in the chain. This phenomenon is known as heteroplasmy. Heteroplasmy occurs when a person has mixed populations of mtDNA in their cells. It's like having two nearly identical versions of a genetic instruction manual. In a normal, homoplasmic individual, all mtDNA molecules are identical. In a heteroplasmic individual, the difference is as subtle as a change in a single nitrogenous base, but the fact that the skeleton showed both versions at once generated an immediate alarm in the forensic community and, consequently, a critical pause in historical validation. The identity challenge. Initially, this genetic trait was interpreted as possible sample contamination, or worse, proof that the skeleton was not Nicholas II's. If an individual has only one mtDNA profile, how could the presumed Tsar show two? The initial conclusion of some analysts was that the identification was incorrect. This scientific doubt once again fueled the historical myth, giving skeptics and believers in Anastasia a reason to doubt the legitimacy of the remains. To resolve the controversy, Russian and American scientists were forced to look for a direct blood relative in the paternal line. The chosen one was Grand Duke George Alexandrovich, Nicholas II's brother, who had died of tuberculosis in 1899 and was buried in St. Petersburg. The exhumation of Grand Duke George was a crucial historical and scientific moment. The analysis of his mtDNA revealed the unthinkable. Grand Duke George also exhibited heteroplasmy at the exact same location in the genetic sequence as Nicholas II. This finding confirmed that heteroplasmy was not contamination, but an inherent and unique genetic trait of that Romanov line. Heteroplasmy, which had been the factor of doubt, became the definitive proof. This hidden trait forced scientists to go beyond standard protocols, rewriting the Tsar's forensic record with an unprecedented level of detail. Despite the initial confirmation of 5 family members, the mystery persisted. The remains of Tsarevich Alexei and one of the Grand Duchesses, later confirmed as Maria, were still missing, fueling speculation of survival. This historical and scientific limbo lasted until the year 2007. In that year, a new discovery near the original mass grave revealed the burned bone fragments of the 2 missing children. This time, the challenge was greater. As the DNA was degraded and fragmented by cremation, scientists turned to nuclear DNA, nDNA, the more complex genetic material inherited from both parents, and Y chromosome DNA, yDNA, which is transmitted exclusively from father to son. Cross-confirmation, Y chromosomal DNA, the yDNA profile of Tsarevich Alexei's remains was compared and confirmed with the yDNA of Nicholas II's skeleton. The paternal line was definitively closed. Mitochondrial DNA, revisited, the mtDNA of the 2 new remains matched the profile of Tsarina Alexandra and the other 3 daughters, proving they were their direct descendants. The 2007 analysis was the final blow. By using the original remains, 1991, as a reference for the missing remains, 2007, science was able to reconstruct the entire family and confirm that the 11 individuals buried in the 2 graves were the totality of the group murdered at Ipatiev House: Nicholas II, Alexandra, Alexei, Olga, Tatiana, Maria, and Anastasia, along with the 4 servants. The hidden trait of Nicholas II's heteroplasmy, combined with the analysis of his brother's remains, marked a watershed moment not only in Romanov history, but in the history of forensic genetics. The end of the myth. The genetic confirmation of the identity of all members of the imperial family put an end to decades of speculation and the legend of Anastasia irrevocably. History in this case was defined by a molecule. Scientific certainty finally buried a myth that had been a recurring theme in popular culture, literature, and cinema for nearly a century. Dignity restored, the identification allowed the Russian Orthodox Church and the state to finally give a dignified and official burial to the imperial family. This act, more than a political event, was a cultural and historical closure for the nation. Scientific certainty provided the basis for an act of historical reconciliation, a forensic precedent. The management of heteroplasmy demonstrated the need for flexibility and depth in forensic genetics. The Romanov case forced scientists to recognize and validate rare genetic variants, setting a new standard of rigor for the identification of ancient or degraded human remains. Today, heteroplasmy is a known phenomenon considered in analyses, largely due to the difficulty it initially presented to the analysis of the last Tsar's DNA. In essence, the re-evaluation of the Romanov DNA did not change the historical event, the execution, but it radically changed the historical certainty surrounding it. Heteroplasmy, that minuscule hidden trait, did not make history different, but it made it definitive. It taught us that, even in the grandest and most tragic narratives, The deepest truth is often hidden in the smallest molecular details, and only the scientific reevaluation of those details can offer a complete historical closure. The Romanov case is the epitome of how science, with its relentless precision, can finally reconcile history, myth, and collective memory. Thus, the Romanov mystery was closed, not by a political decree, but by a double DNA sequence. Heteroplasmy, the trait that almost disqualified the remains, became the unique signature of the last Tsar, proving that historical truth sometimes waits in the smallest details of our biology. What other secrets do you think science should solve? Leave it in the comments. If you enjoyed this journey through the past and genetics, share this video, and be sure to subscribe so we can continue unearthing stories together.